Good evening and welcome to the Calculus 2 final exam review session. My plan is to go through the two practice final exams, which you can find on Canvas, and I'm happy to answer any other questions. So as always, if you have questions about anything, send me a message in the chat or send me an email, and let's get started. I guess I have to fix the topic. We're not solving differential equations with power series tonight. We are just doing some final exam review. There we go. All right, so I'm going to start with the fall 2022 final exam. All right, multiple choice. Each of these is an example of an alternating series for which all of the all of the ANs are positive, meaning that the series actually does alternate. And then AN is greater than AN plus 1, meaning that the terms are decreasing in magnitude. And then the alternating series diverges. Okay, so we've got some options here. Now I'm just thinking about, why does this not imply, why do these conditions not imply that the series converges? This reminds me of the alternating series test. But there's one condition that's missing, so that we can't apply the alternating series test, and it's that we would need the series terms to approach 0. If we also knew this, then the series could not possibly diverge. It would have to converge. And since we don't know that, we could have a divergent series. Let's see. So let me look through the options and see which one has positive terms. This is going to be positive. Oh, that's not positive. That's alternating. This piece is alternating, which means the whole thing is positive. This is the sum of just 1 over n. Okay, so it's not B because the ANs are not positive. Cosine pi n. That does alternate between 1 and negative 1. So that one alternates, and the series terms are decreasing, so it would satisfy the first 2 bullet points. But the series actually converges, because this 1 over n squared does approach 0. So it's not C. This is positive also. So when we look at this condition next, are these series terms decreasing? They are decreasing here, and it's a little harder to say here. But I do believe that these terms are approaching infinity. Because an n power is going to, like n to the n is going to get bigger faster than that n factorial. So I don't think it's D, but let's just check that all the conditions are correct for A. I think we've already said this is positive and decreasing. Does it diverge? Yes. It diverges because this 1 plus over n is approaching 1. So when n is really big, these series terms are essentially alternating between 1 and negative 1. And by the divergence test, that's going to diverge. So option A. It's the area bounded by the polar curve r equals 1 plus cosine theta. Okay, let me sketch a quick graph of this. I have a recollection that this is a circle, but I'm not 100% sure where a circle is. I think it's over here in the first and fourth quadrants, but in case you forget exactly what this looks like, we can just plug in a few values of theta to get a rough idea. So when theta is 0, cosine of theta, the cosine of 0 is 1, so the radius is going to be 1 plus 1, which is 2. When theta is pi over 2, the cosine is 0, so r is going to be 1. This is not a circle. Oh, sorry, cosine is 0. So as theta increases from 0 up to pi over 2, the radius is decreasing. No, sorry, r is 1. Cosine, let me write this. Cosine of pi over 2, well, 1 plus cosine of pi over 2 is 1 plus 0, which is 1. And cosine is 3 pi over 2. The cosine is going to again be 0. So the radius will again be 1. And at pi, the cosine is negative 1, so r is 0. So it's going to look like this, I believe. Let me just confirm it doesn't. Yeah, that looks about right. How do you get a circle? Does it have to be sine theta? No. Oh, you don't have the 1 plus, right? Is it just r equals cosine theta? Yeah, that's how you get a circle. Okay. So, to find the area, I'm going to integrate over the interval from 0 to 2 pi with respect to theta. And the area of a little slice of this shape the area is going to be 1/2 r squared d theta. Alright, so I'm adding up the angles of all those little slices, which means integrating 1/2 r squared d theta from 0 to 2 pi. And r is 1 plus cosine theta. It did not give me a lot of room here to do this integral. Let me throw that up there in the previous problem. I'm going to expand out this 1 plus cosine theta squared. And then I'm going to split this up into 3 integrals. One is just the integral of 1 d theta. The second one is the integral of just cosine theta, where I've canceled out the 1/2 and the 2. And then finally, I have an integral of cosine squared theta. That first integral is just 2 pi. The second integral, I'm going to use the antiderivative, which is sine of theta. But when I plug in 0 or 2 pi, those both give me 0. So the second term doesn't contribute anything to the integral. And then lastly, I'm going to rewrite cosine squared of theta as 1 plus cosine of 2 theta over 2. So I've got pi plus 1/4 times the integral from 0 to 2 pi of 1 plus cosine of 2 theta. And my antiderivative is going to be theta plus 1/2 times the sine of 2 theta. Once again, when I plug in the 0 and the 2 pi, I'm going to get 0 from that sine term. So all that's left is pi plus 1/4 times 2 pi minus 0. That is pi plus pi over 2, which is 3 pi over 2. Hi, Kendall. How are you this evening? Okay, so we're rewriting this integral using trig substitution, and they're not going to make us evaluate it all the way out because it's going to involve a secant. I don't even remember the antiderivative of secant off of the top of my head, but they're suggesting that we use. Oh, wow! They're even telling us what trig substitution to use. X equals tangent theta. So dx is secant squared theta d theta. I'm going to need to convert the bounds also. So when Yeah, so if x is tan theta, then theta is the inverse tangent of x. So when x is 0, theta is the inverse tangent of 0, which is 0. And when when x is 1 over root 3, when x is 1 over root 3, theta is the inverse tangent of 1 over root 3, which is 30 degrees, or pi over 6. Okay, so the integral is the integral from 0 to pi over 6 of 1 over 1 plus tangent squared theta times dx, which is secant squared theta d theta. I'm pretty sure this is going to simplify down to just secant of theta. I don't see any way to get a 2 theta into here, but let's just work through the details. I don't know why I switched from blue to black. I'll switch back after this problem. So I need to simplify this 1 plus tangent squared. I never remember that identity exactly. The one I do remember is sine squared theta plus cosine squared theta equals 1. If I want to get a tangent into this, I need to divide both sides by cosine squared theta, so that I get the sine squared over cosine squared. That is tangent squared theta. Cosine squared over cosine squared is 1. And the reciprocal of cosine squared theta is secant squared theta. Okay, so indeed, that square root in the denominator, inside that we're just going to have secant squared theta. So the square root is going to cancel out that 2, and then the secant theta is going to cancel out one of the secant thetas. That just leaves us with secant theta. So it should be option C. Alright, suppose the power series, I covered that up a little bit. Suppose the power series, sum from n equals 1 to infinity of an x plus 4 to the n converges at x equals negative 7 and diverges at x equals 3. What can we say about the convergence or divergence of the series, just the sum of a n? Okay, well, what's the connection between this and this? Well, there's a certain x value that you can plug in to this power series to get just the sum of these coefficients. That x value would, of course, be negative 3. Because negative 3 plus 4 is 1. Okay, so let me make a little number line. We're told that the series converges at negative 7. And diverges at x equals 3. And it's this power series is centered at x equals negative 4. That's the center of my interval of convergence, -4. And we're asking whether the series converges at x equals -3. It's definitely going to converge at -3. And I know that because the radius of convergence has to be at least 3, so it's going to converge at least everywhere from -7 up to -1. I know that the radius of convergence is at most, well, it's less than 7, because 7 units to the right, up at x equals 3, the series is diverging. But right here at -3, it is still converging. So option A is the correct answer. Right, which of the following integrals represents the volume of the solid of revolution formed by rotating the region bounded by the x-axis and this parabola around the y-axis using shells? Okay, let's graph this parabola. If you factor that, that would be x times 1 minus x. So 0 and 1 are the roots of that parabola. And it opens downward. So it looks like this is the region that we're rotating around the y-axis. So we're rotating it around the y-axis. They want us to use shells. You would get shells by slicing it this way. And that is integrating with respect to x. Because when you rotate that thin vertical slice around the y-axis, well, yeah, you're going to get a shell. If you were to slice it instead horizontally and rotate that around, you would get a washer. Okay, so if this is x, I'm going to think about the volume of that cylindrical shell. And the way we think about that is if we sliced it open and then unwrapped it, it would essentially be a rectangular prism. The volume, the volume of the rectangular prism is the length times the width times the height. So I guess the thickness of that would be dx, and then the height is f of x, which is x minus x squared. And the length of that unwrapped rectangular prism is the circumference of the circle, which is 2 pi times the radius, and the radius there is x. So this should be the volume of that red cylindrical shell. To get the total volume of this shape, I integrate from 0 to 1. That looks like option C. All right. That's a lot of equations. Okay. Which equality should be used to compute the following integral using partial fractions? Oh, okay. So because of this 2 minus x squared, there should be a fraction with a 2 minus x in the denominator, and then also a 2 minus x squared. So I don't see that in options A, B, or D. I only see that in C and E. And then for this 1 plus x squared, the numerator does need to be a linear term. So option C is correct. Okay. Third degree Taylor polynomial centered at a equals 2 for 1 over x. Alright, so I need the first 3 derivatives of f at 2. I'm going to rewrite f as x to the minus 1 to make it a little bit easier to take these derivatives, which I do by just repeatedly applying the power rule. And now let's plug in 2 to all of these derivatives. Okay, and then the Taylor polynomial is f of 2 plus f prime of 2 times x minus 2 plus 1/2 f prime of 2, and that's 1 over 2 factorial, which is the same as 1/2, times x minus 2 squared, and then 1 over 3 factorial f triple prime of 2 times x minus 2 cubed. That first term is 1/2. That's f of 2. I see that in all 5 options. The second term is minus 1/4 times x minus 2. I see that again in all 4 options. The third term is 1/4 times 1/2, so it's 1/8 times x minus 2 squared, and only option B has that 1/8. We could also check the last term just for fun. It would be 1 over 6 times minus 3/8 x minus 2 cubed. That is minus 1/16 x minus 2 cubed, which is in fact what we have here in option B. All right. Which of the following is a plot of r equals 1 plus 2 sine theta? Okay. So when I plug in theta equals 0, r is going to be 1 plus 2 times the sine of 0. Sine of 0 is 0, so r is just 1. I guess that rules out option D, because r is definitely not positive 1 here. Could that be positive 1? Could that be positive 1? Could that be positive 1? Yeah, probably they all are. So what about when theta is pi over 2? Sine of pi over 2 is 1, so r is going to be 3. So as we go from 0 to pi over 2, the radius increases from 1 to 3. That is definitely happening in A. It's not happening in option C. The radius is decreasing to 0. And in option B, it's also decreasing to 0. So it's got to be option A. Okay, find the slope of the tangent line to this parametric curve at 3, 1. Right, the way that I find the slope of the tangent line, which is dy dx, when I have a parametric curve, is I do dy dt divided by dx dt. And it's kind of like the dt's cancel out. Not literally, it's actually the chain rule, but yeah, so the derivative dy dt is just e to the t minus 1, and then dx dt is 2t. And at, oh, I guess we have to find the value of t. That gives us the point 3, 1. The y value is going to help us out. We could also try to solve with the x value too, but if I know that the y value of e to the t minus 1 is equal to 1, then taking the ln of both sides, I get t minus 1 equals 0, so t is 1. And if we confirm when we plug in x equals 1, or t equals 1 to the x equation, we get 1 squared plus 2, which is 3, as we expected. Okay, so t equals 1 is the time when we pass through the point 3, 1. And at time 1, dy dx is e to the 1 minus 1 over 2 times 1. That's 1 over 2. So 1/2 is the slope. Hello, Rabid Marine. Thanks for joining us. Couldn't write down the last two ones. I have to see an ad because I logged. Oh. Yes, I'm going kind of fast. My recommendation is, so the recording will be available afterward, so you can watch through anything that you want to see again, and then pause as you need to. I'm also happy to slow down and re-explain anything. If you have any questions, just let me know. So any questions so far? Anything you'd like me to go back and take another look at? Oh, good question. Should you spend more time writing or listening? My recommendation is probably just to spend more time listening and trying to follow along with the ideas. But that's what I would do. But yeah. Okay, let me move on then, but again, I'm happy to go back and clarify anything where I went too fast. Okay, so we're going to determine the behavior of these series and identify which tests we would use to show convergence or divergence. And they make this point, so yeah, sometimes multiple tests will work, but we only need to write one test. Okay, sum of 1 over n root ln of n. That's going to be an integral test for sure. So my idea here is to evaluate the integral from 2 to infinity of 1 over x root ln of x by using a u sub. I'm going to substitute u equals ln of x. So du is 1 over x dx. So this is the integral from, okay, I do have to change the bounds. It doesn't matter for determining convergence, but let's just get the details right here. It does become the integral from ln of 2 to infinity of 1 over root u du. And the du is this 1 over x dx. Yeah. And Rapid Marine, the ideal scenario would be that you have already worked through these practice exams and we're sort of, we're going through these together and you're checking your work. But I did, have to, at the last minute, move the stream up from tomorrow to today. So I can't blame you if you haven't had time yet to work through these practice exams. Let's see. So if we're being technically correct, we should write this as a limit of proper integrals. They're not really looking at your work here. You don't need to show your work. So if you can just look at this and tell whether this is going to converge or diverge, then you wouldn't even need to show all this work. We could rewrite this using an antiderivative. Our antiderivative would be 2 root u that's going to go to infinity. Yeah, but Rapid Marine, that's like the ideal scenario. I'm sure anyone who's watching who has not yet worked through these practice exams, you should still be able to get quite a lot out of this, I hope. Let's see, so infinity, so this series diverges. One other idea that occurs to me is when I see this 1 over root u, this integral is going to converge if and only if the series 1 over root n converges, and I just know that that one diverges by the p-series test, with p equal to 1/2. So there's another way to see that the series diverges. Okay, 1 plus sine of n over n squared. That 1 plus sine n, I know that's trapped between 0 and 2 because sine of n is always between 0 or negative 1 and 1. So that means that 1 plus sine n over n squared is less than or equal to 2 over n squared. So I would do a direct comparison test. I guess they wrote the word test here, so I don't need to write test again. So I wrote integral test test. But since my series is less than a convergent series. This one converges also. Okay. Arctangent of n squared. The arctangent graph looks kind of like this. It has horizontal asymptotes at pi over 2 and negative pi over 2. So as n goes to infinity, arctangent of n is approaching 1. That means this diverges by the divergence test. The series terms are not approaching 0. So the series could not possibly converge. Okay, next up we have n log n over 7 minus 11n plus n squared. The fact that the denominator is so complicated makes me think that I want to do a limit comparison test. Like maybe I want to do a limit comparison with something simpler like n log n over n squared, which is log n over n. Oh, yeah, log n over n. That one definitely diverges. For one, because it's bigger than 1 over n, which diverges. So this one diverges, and the limit comparison test will tell us that. Okay. I've got a definite integral. We're into the free response now. This looks like a classic integration by parts problem. I'm going to let u be x squared and dv be e to the x dx, so that v is e to the x, du is 2x dx. And my integral is going to become uv, evaluated from 0 to 1, minus the integral of v du from 0 to 1. When you plug in 1, you get 1 squared times e, which is e, and when you plug in 0, that x squared makes this 0. So once again, we're gonna have to do integration by parts again. I'm gonna pull that 2 outside the integral. And then when I integrate by parts again, I've got u equals x, so du is dx, dv is e to the x dx, meaning v is e to the x. And when we apply integration by parts, we'll get uv, which is x e to the x, evaluated from 0 to 1, minus the integral from 0 to 1 of v du, which is e to the x dx. So I get e minus 2 times, once again, we get e minus 0. And then my antiderivative of e to the x is e to the x. Evaluate it from 0 to 1. I get e minus 2 times e minus, oh, that's so many minus signs in parentheses, but that's going to be e minus e to the 0, which is 1. That's e minus 2 times e minus e plus 1. The e's cancel, and I get e minus 2 times 1, or e minus 2. Okay, let me ask Wolfram Alpha to double check this for me. Obviously, you can't do that on the exam, but I'm allowed to do that during the review session. I'd hate to make a mistake and not correct it. E minus 2 is the correct answer. Okay. So integration by parts twice. Okay, third degree Taylor polynomial of sine of x centered at pi over 2. All right, we've already done a Taylor polynomial. So what we did was we found the first 3 derivatives. It's pretty easy with sine because the derivatives just cycle through sine, cosine, minus sine, and minus cosine. When we plug in pi over 2, we get 1, 0, negative 1, and 0. So the Taylor polynomial, the third degree Taylor polynomial for sine x is 1. Then there's no x term. And then there's a minus 1 times 1 over 2 factorial times x minus pi over 2 squared. And then there's no degree 3 term because that coefficient would be 0. So it's just 1 minus 1/2 x minus pi over 2 squared. Oh, and there's I can't resist pointing this out, there's a clever way to do this. We're trying to essentially say what sine of x minus 2 is. Sorry, sine of x minus pi over 2. Which is, I'm going to pull a minus sign outside of the sine. I can do that with sine, not with cosine, but with sine. I can pull a negative sign out. That leaves behind sine of pi over 2 minus x, but that is just cosine of x. I think I'm overcomplicating this. Am I? I wanted to use the power series for cosine of x. So this 1 over 1 minus 1/2 times x minus pi over 2 squared, that really looks like the first couple terms of cosine of x just shifted. Huh. I'm missing something, but it's not super important. We can compute this Taylor polynomial just by computing those derivatives and using the formula for the third degree Taylor polynomial. Okay, so now we want to approximate sine of 1. 1 is kind of close to pi over 2, which is where we've centered this Taylor series. Pi over 2 is about 1.57, so 1 is not super close, but kind of close. But the idea is that we're just going to plug in 1. So sine of 1 should be approximately equal to t3 of 1, which is 1 minus 1/2 times 1 minus pi over 2 squared. That's it. Taylor's inequality to give an upper bound for the error. Okay. I have to remind myself what Taylor's inequality says because I have not been studying up for the Calc 2 final recently. Okay, so Taylor's inequality says that if the n plus first derivative is bounded by m, I'm not writing out all the details, but yeah, if it's bounded on some interval, then the remainder is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. In our case, we can take m to be 1 because the n plus first derivative, well, I guess in our case, n is 3. We're using the third degree Taylor polynomial, so the fourth derivative of x is going to be bounded by a constant, and that would tell us that the error in using the third degree Taylor polynomial is bounded by this. In our case, we can take m to be 1 because that fourth derivative is sine of x. What do I know about sine of x? It's between negative 1 and 1. So the error is going to be bounded by 1 over 4 factorial times 1 minus pi over 2 to the fourth. That's what Taylor's inequality says. Okay. 3-meter tall skate park in Boulder was hit by a recent snowstorm. Could have been this year. Not a lot of snow this season. The section is filled with densely packed snow. They give us a density up to a height of 2 meters. We want to compute the work needed for Boulder Parks and Rec to remove all of the snow by bringing it to the top section of the skate park. Okay, so we're going to want to work with a coordinate system probably where 0 is the bottom of the skate park. I'm going to use y as my variable. So this is y equals 2, and the top is y equals 3. Oh, I guess that goes off the screen. Y equals 3. So I want to think about sort of a horizontal slab of the snow at some height y. the work that it takes to get it out of the tank, I'll call it dW, it's the work, but I'm just looking at an infinitesimal slice. Work is force, which I'll call dF, times distance. Force, well, we are counteracting the gravitational force when we lift this out. And the force is the mass times g, the gravitational constant. And then mass is density. I think they called it rho. Yep, density times volume. Okay, so now let's think about what all of these are. I'm just going to gather the constants up front. I've got a rho, a g, and then a dv. The volume is going to be length times width times height. The height is the easy part because it's just dy. And I guess the that width is also easy because it's this constant 5 meters. It doesn't matter whether I'm looking at a slab down at the bottom or when near the top. That width is always 5 meters. The hard part is the length here, because that changes when I'm looking at different slabs. So for the bottom one, it's 6 meters. For the top slab, actually it's not even so obvious. If we looked at the very, very top where there isn't snow, but if there were up here, it would be that 6 meters plus another 3 meters and another 3 meters, so it would be 12 meters. So I guess the formula would be, it's going to be 6 meters plus something times y. So when y is 3, we're supposed to get 12. So 6 plus 3 times what would give me 12? 6 plus 3 times 2 would give me 12. So 6 meters plus 2y. So that's the work that it... Oh, wait. Sorry, I ignored the distance. The distance from this slab at a height of y up to the top of the skate park at a height of 3, the distance is going to be 3 minus y. Or 3 meters minus y. So that is the work required to lift this one slab of snow up out of the skate park. To do that, or to find the total work, we just add up the result for all of the slabs from a y value of 0 up to a y value of 2 meters. And there we go. Okay. I've got a power series. I want to find the radius and interval of convergence. Okay. I just see x to the n. It's not x minus something to the n or x plus something to the n. So the interval of convergence is going to be centered at x equals 0. So we'll start by using the ratio test to try to get a feel for what the radius of convergence is. So we'll look at the limit as n goes to infinity of, and let's call this term an. So absolute value of an plus 1 over an. That gives us x to the n plus 1 over n plus 1 times 4 to the n plus 1 over x to the n over n times 4 to the n. Let's begin by rewriting this quotient of fractions. Dividing by a fraction is the same thing as multiplying by its reciprocal. And then a lot of stuff cancels out. x to the n plus 1 over x to the n is just x. 4 to the n over 4 to the n plus 1 is 1/4. And then we have the n and the n plus 1. I can simplify this to absolute value of x over 4 times n over n plus 1. Basically, all of that is positive, so it can come outside the absolute value. That x could be positive or negative, so we need to keep it inside the absolute value. And I guess I can split this up into two limits. And n over n plus 1. That's going to approach 1. Oh, and I guess I'm even overcomplicating this a little bit. This x, absolute value of x over 4, doesn't have an n in it. So as far as the limit is concerned, that's a constant. It just comes outside of the limit. So we get the absolute value of x over 4. Okay, so the series converges if this limit is less than 1. That's what the ratio test says. If the limit is less than 1, the series converges. That's the same thing as the absolute value of x being less than 4, which is the same thing as x being between -4 and 4. The series diverges if the limit is greater than 1, which happens if x is less than -4 or x is greater than 4. Okay, so the radius of convergence is 4. The interval, we're not quite sure about just yet. because the ratio test doesn't tell us what happens when the limit is 1, which means it doesn't tell us what happens at x equals -4 and at x equals 4. For those two cases, we're just going to have to plug in the x value and analyze that series separately. Okay, so when x is 4, we have the sum from 1 to infinity of 4 to the n over n times 4 to the n. But the 4 to the n's cancel, so we're just looking at the sum from n equals 1 to infinity of 1 over n. That's the harmonic series that diverges. So the series does not converge at 4. At x equals -4, however, we get minus 4 to the n over n times 4 to the n. That's the same thing if I expand the numerator as -1 to the n times 4 to the n over n times 4 to the n. Once again, the 4 to the n's cancel, but this time I have a -1 to the n. This is the alternating harmonic series, which does converge. So the series converges at x equals -4, but not at x equals 4. All right. Okay, so they want us to use a Taylor series for arctangent of x to find a Taylor series for x to the 4th arctangent of x cubed. Alright, I don't remember the series for arctangent of x off the top of my head, so let me rederive it. The thing that I do remember is that 1 over 1 minus x is 1 plus x squared plus x cubed, and so on. Or in sigma notation, it's the sum from n equals 0 to infinity of x to the n. So this is a geometric series, and if x is less than 1, then it converges to the initial term over 1 minus the common ratio. So that's what I do remember. And then the connection with arctangent is that the derivative of arctangent of x is 1 over 1 plus x squared, which looks kind of like that. I could rewrite this as 1 minus 1, or 1 over 1 minus the opposite of x squared. So the idea is that if I substitute that minus x squared in right here, this is the sum of of minus x squared to the n, which is minus 1 to the n, x to the 2n. So that's the derivative of arctangent of x, which means that arctangent of x is the antiderivative of this. So when you anti-differentiate x to the 2n, you get x to the 2n plus 1 over 2n plus 1. Okay. Probably you should just have this formula, this power series for arctangent of x memorized. I definitely made this a little harder for myself by not recalling that, but it's nice to remember where it comes from also. Okay, so arctangent of x cubed would be the same thing, except that I replace the x with an x cubed. X cubed to the 3n plus 1 is x to the 6n plus 3. And then to find the power series for x to the 4th arctangent of x cubed, I just multiply an x to the 4th with the power series for arctangent of x cubed. I'm multiplying an x to the 4th with the existing expression, and that's just going to add a 4 to the exponent. That is x to the 6n plus 3 times x to the 4th is x to the 6n plus 7. Okay, so now I'm trying to find the 19th derivative of my function, x to the 4th arctangent of x cubed, evaluated at 0. And I can do that because I know that in the power series, maybe I'll call it t of x. It's f of 0 plus f prime of 0 times x plus, and so on. And then eventually we're going to get to a term which is the 19th derivative of f at 0 divided by 19 factorial times x to the 19th. And then it'll continue on. But I just need to identify the term in that sum which matches up with this, which has an x to the 19th. That's going to happen when 6n plus 7 is equal to 19, which happens when 6n is 12, where n is 2. And the n equals 2 term of this series is minus 1 to the 2 over x to the 19, times x to the 19 over 2 times 2 plus 1. So that's minus 1/5 x to the 19th. So that was supposed to be this term, which means the 19th derivative of f evaluated at 0 over 19 factorial times x to the 19th is equal to minus 1/5. Wait, minus? What am I talking about? Where'd the minus come from? Minus 1 squared is positive 1, not negative 1. So 1/5 x to the 19th. Cancel the x to the 19th. We have f to the 19th derivative of f at 0 over 19 factorial is 1/5. And that tells us that this 19th derivative is 19 factorial over 5. Alright, second to last page. Find the implicit solution to the initial value problem. Okay, so let me first rewrite the dy dt, or the y prime as dy dt. And then I'm going to cross multiply, so I get 3y squared plus 2 dy is t plus 1 dt. And then I'm going to integrate both sides. So we'll get y cubed plus 2y equals 1/2 t squared plus t. I gotta throw on a constant. I don't need to put on a constant on both sides because I could just subtract over and end up with a constant, with a single constant on one side of the equation. But they also tell me that when t is 2, y is 1. So when I plug in 1 for y and 2 for t, I'm going to be able to solve for the value of c. So I have 1 plus 2, which is 3. That's equal to 1/2 times 4, which is 2 plus c. So it looks like c is going to be -1. So the solution here is 3y squared plus 2, oops, sorry, copying the wrong line. I should be looking at this. Y cubed plus 2y equals 1/2 t squared plus t minus 1. And when they say implicit solution, they just mean that I don't need to solve this for y. I don't need to get it to be in the form y equals a function of t. I can just leave it like this. Okay, that brings us to the final page. They want us to show that this series converges. I think there are a lot of ways to do this. I think I'm going to do the ratio test because that should be the easiest. That should be the easiest. But I just want to point out, you could also use the alternating series test. This whole denominator is positive. And then the -1 to the n means that it alternates. 3 to the n times 2n plus 1, that is definitely decreasing. And these series terms are approaching 0. So you could use the alternating series test. I'm just going to use the limit, or the ratio test. So let me take the ratio of an plus 1 over an. Yeah, does the alternating series test, do you mean like does the function have to be continuous? No, I think the integral test requires the function to be continuous. But you wouldn't need that here. So yeah, Barry the Bee agrees with me. You could use the alternating series test here. But then you have to like write down all those conditions, like check all the conditions that the test applies. I kind of just like the ratio test. It's very straightforward. I compute the limit, and if it's less than 1, I know the series converges. So I'm going to have a -1 to the n plus 1 over 3 to the n plus 1 times 2n plus 3. I plugged in an n plus 1 there and just distributed. Divided by an, so that's going to be times 3 to the n times 2n plus 1 over minus 1 to the n. We're going to end up with 1/3 from the 3 to the n and the 3n plus 1, and then a 2n plus 1 and a 2n plus 3, and the negative 1, the powers of negative 1 are just going to get killed by the absolute value signs. So the 1/3 is a constant, meaning that it can come outside of the limit. I'm left with 2n plus 1 over 2n plus 3. That limit is 1. So overall, the limit is 1/3. And that means that by the ratio test, the series converges. Oh, hey Zach. How are you doing tonight? We're just doing some Calc 2 review for the final exam, which I believe is on Wednesday. So this is my truly my final math stream of the semester. Okay, then we want to use the Taylor series for arctangent of x to find the value that this series converges to. Yeah, so we just discussed the power series for arctangent of x. I did not remember what it was, but we deduced from the geometric series that it is... I already forgot. Is there a minus 1 to the n? There is, right? Minus 1 to the n, x to the 2n over 2n plus 1. Let me just confirm. Yes. What's the distribution of the final exam? You know, I actually don't know off the top of my head because I'm not teaching Calc 2 here this semester. I actually haven't taught it in 2 years. So normally with our, I taught Calc 1 here for the last 5 semesters, and we always emphasize the last portion of the course a little more, like between the 3 midterms worth of material in the final exam. It would be like a 20-20-20-40 distribution. But in Calc 2, I guess y'all have not really covered a whole lot of material since the 3rd exam, right? Ooh, any vector arithmetic stuff? I don't believe they do that in Calc 2. I think we do all of the vector stuff in Calc 3. And I guess for anyone watching, I should give a shout out to Ida, the 2iPi. I don't have a bot set up here to like do the actual shout out in the Twitch chat, but either the 2iPi is another math streamer. You all should give him a follow. He streams way more regularly than I do. So yeah. I guess Zach, is your streaming at all tied to the academic calendar, or do you just keep going throughout the summer at the same rate? You just keep going. Okay. Well, for anyone watching, if you wanna keep learning about some math, just stay sharp over the summer before, for example, if you're moving on to Calc 3, if you wanna, make sure that you don't forget all of it before the fall semester. Follow e to the 2i pi. Check out his streams. Break after Thanksgiving before New Year's. Yeah, that's a great time to take a break. I had a friend who went to a college where they were in a quarter system, and they wrapped up their fall semester before Thanksgiving and then had 6 weeks off for winter break. That sounds fantastic. Are we done with the Calc 2 review? Almost. We're on the last question. We were just trying to find the value that this series converges to. So this series, let me just copy it down here. It looks really similar to the power series for arctangent of x. Oh, sorry, there wasn't even an x to the 2n. Here we go. So we're looking for a value of x that would make these match up exactly. I see the 3 to the n down here, but there's nothing like that up there. So what if I bring that 3 to the n up into the numerator? And maybe let me even write that as 1/3 to the n. Now this almost matches up, except there's a 2n and an n. So the way that I can fix this is, well, what do I need to put here? Right, what do I need to raise to the 2n in order to get the same thing as 1/3 to the n? I guess I can kind of cancel those powers of n out. I actually need to put the square root of 1/3. Inside those parentheses. Oh, yeah, Rabbit Marine, glad to hear it was helpful. Thanks for watching. And as we're wrapping up, if anyone has any last questions, anything you'd like me to talk more about, I'd be happy to. I don't think that I'm going to have time to go through the other practice midterm, since we've been going for about an hour and a half just doing this one practice midterm. But if there are any particular few questions that anyone would like me to look at, I'm happy to do just a few more. But we are wrapping up this question here. Our series matches up with the series for arctangent where the value of x is 1/√3. So what angle gives me an arctangent of 1/√3? We saw this actually somewhere toward the beginning of this exam. It was pi/6. So this series converges to pi/6. All right, any last questions? Number 15 on the other exam. Yeah, again, I'm happy to do a few questions from this other exam. So if there are any particular topics you'd like a little more practice with, let me know. Find a power series centered at 0 that represents the function x over 2 plus x. Oh, yeah, okay. So, just like with this last one of our basic building blocks for power series is the series for 1 over 1 minus x, which is this geometric series, the sum of x to the n. So I'm trying to get this x over 2 plus x to look something like that. So the first and easiest thing that we can do is to just sort of pull the x out. So now at least I have the right numerator. And we saw an example like with the x to the 4th arctangent of x cubed. We saw that if you want to multiply your function by x to the 4th, you just multiply the power series by x to the 4th. Same thing here. We'll find the power series for this and just multiply by x. I want a minus, not a plus. So the next thing that I'm going to do is to rewrite 2 plus x as 2 minus negative x. Okay, so I fixed the numerator. I fixed the sign in the denominator. The only problem is that I have a 2 in the denominator instead of a 1. How can I fix that? I could pull out a 1/2. Of course, I have to pull the 1/2 out, or pull the 2 out in the denominator from both terms, both the 2 and the minus x over 2. So now I have a minus x over 2. That's fine. Now I really do have this in the form 1 over 1 minus something. So I can replace that with this power series, the geometric power series. But I'm plugging in minus x over 2 for x. If we distribute the nth power, we get minus 1 to the n times x to the n over 2 to the n. And then when we bring in that 1/2 x, we're going to get minus 1 to the n, x to the n plus 1 over 2 to the n plus 1. So here's a power series for 2 over 2 plus x. They also wanted us to find the interval of convergence for the power series. So I know that the geometric series converges on the interval from -1 to 1, not including either end point. I'm going to slightly rephrase this. It converges when x is between -1 and 1. I'm going to slightly rephrase that one more time for convenience when I come down and think about this power series. It converges when the absolute value of x is less than 1. So when I make this jump here, when I use that power series, when is this geometric power series going to converge? It's going to converge when that thing is less than 1 in absolute magnitude, absolute value, the minus x over 2. So that's the same thing as the absolute value of x over 2. So absolute value of x is less than 2, and that means -2 is less than x is less than 2. So the interval of convergence is -2 to 2, not including either endpoint. If you use the ratio test like we did in the example on the other midterm, right, you could just take this series and you could apply the ratio test there. You would find the same answer. All right, any last questions? Oh, okay. I guess I can give shoutouts without a bot installed. I thought it was a bot that was doing that, but yeah. So go follow Eda the 2iPie. He will continue streaming throughout the summer, whereas I am done for now, at least. Oh, see, I always see people doing !SO for shout out. That's why I thought that you needed a bot, but well, now I know. Am I still teaching at CU next year? No, Barry. I'm a teaching postdoc, so my term here was just for 3 years, and this unfortunately is my third and final year. So this is it for me. Moving to Virginia over the summer. I got a job offer from a small liberal arts college there. I don't want to say which, just because it's not official yet. I haven't signed the contract yet, but yeah, I'm excited to be continuing to teach math, even if I don't get to live in Colorado. They still have some mountains out in Virginia. I hear it's pretty nice. Thanks, Buried the Bee, and good luck to you too. I do think I will continue to do some streaming on Twitch. Got some ideas. Haven't figured out exactly what that looks like, but yeah, for anyone who's interested, if you're following me, so you get notifications if I go live, I do plan to continue bringing some mathematical content to you going forward. But yeah, I'm also excited for a little bit of the break. I'm ready for it to be summer break. One more week, and we can all relax. Okay. Well, if there are not any last-minute questions, I think I will wrap up. We'll call it a night. I wish you all the best of luck on the Calc 2 final and with the rest of your final exams. I hope you have a great summer. And yeah. I don't really have anything else. Good luck with finals. Have a great summer. Thanks for watching. And good night.